Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important topic. The topic is, let me write the topic. Our topic today is Compton Effect. So let us discuss this effect. Compton is the name of the person. The complete name of the person is Arthur Holly Compton. Arthur H. Compton. This effect is after his name because he was the first in the early 1920s to describe this phenomenon, which we are going to discuss. Now, what is Compton effect? It is the scattering of a photon by an electron, right? The scattering of a photon by an electron, this phenomenon is called Compton effect. Remember what is photon? Photon is the energy particle. In the discussion of photoelectric effect, we said light under certain circumstances behaves like a stream of particles, and those particles which are localized energy bundles are called photons. So photon is a light particle, and according to quantum theory of light, photon behaves like particles except for their lack of rest mass. By that I mean a photon is as good as a materialistic particle like electron, but it has only one thing different from some materialistic particle like electron or proton or some other materialistic particle, that it lacks rest mass. Let me write it. Photon behaves like particles except for its lack of rest. So it has no rest mass, right? But it behaves like particles. So in this Compton effect, what happens? Let me first draw a rough diagram. I have some target electron. Now there comes a photon. This is my photon. When it hits this electron, let me use another color. This photon gets scattered. So let me write here, it is scattered photon. Let me get red color. It is my incident photon. In this process, this electron also gets scattered. Let me use some other color for it. Uh, Let me use this one. Now, this electron also gets scattered. So it is scattered electron, right? This is the process of Compton. There is a target electron. Now in comes incident photon. It hits the target electron. Electron gets scattered and the photon gets scattered, right? So you can see this appears to be like some striker in carom board striking some carom coin. The carom coin gets scattered in one direction and the striker gets scattered in another direction. You can see when I say photon behaves like particles, it behaves like materialistic particles because the phenomena it shows are like materialistic particles. But it has only one thing different than these materialistic particles. It doesn't have any rest mass, right? Now, in this phenomenon, this incident photon has some energy. For example, let its energy be, we know photon's energy is h nu, where h is Planck's constant, nu is the frequency of the wave. So this incident photon has some energy. When it hits this target electron, it loses some energy because some of the energy gets transferred to this target electron. Therefore, this scattered photon has different energy. So if the energy of the scattered photon, it will be different. It will be h nu prime. So the energy of the scattered photon is different, and that is reflected in its different frequency. So here nu prime is the frequency of the scattered photon, and nu is the frequency of the incident photon. So scattered photon has less energy than incident photon. So h nu is greater than h nu prime because incident photon has lost some of its energy. It is greater. Scattered photon has smaller energy. It has lost some of the energy to the electron. But the total energy remains conserved in this phenomenon. Total momentum remains conserved in this phenomenon. So what Compton did? Now, if lambda is the wavelength of the incident photon and lambda prime is the wavelength of the scattered photon, we know frequency and wavelength are inversely proportional. Nu is greater than nu prime, but lambda will be less than lambda prime. That means lambda prime is greater than lambda. That means scattered photons frequency is smaller, but scattered photons wavelength will be greater than the wavelength of incident photon. What Arthur Holly Compton did, he predicted the shift in the wavelength of the photon, that is lambda prime minus lambda. He calculated this shift in the wavelength. He predicted it to be some expression. We will derive that this lambda minus lambda prime, that is the increase in the wavelength of the photon in this phenomenon, or I should say the amount by which the wavelength of the photon increases, he got the expression for this. This shift in the wavelength or change in the wavelength of the photon is called Compton shift. Compton shift. Now we will derive expression of this Compton shift as it was done by Arthur Holly Compton, right? So now you know this phenomenon. It is the scattering of a photon by an electron, and in this phenomenon, we have an incident photon which hits an electron, then it gets scattered, electron gets scattered. In the process, energy is lost, and that lost energy is taken by the scattered electron. The wavelength of the scattered photon is greater than the wavelength of the incident photon, and that change in the wavelength is called Compton shift. So let me move to find the expression for this Compton shift, and you know that in any such scattering event, when we have to predict some things after collision, we use the two main laws, that is law of conservation of energy and law of conservation of linear momentum. So we will use those two laws to find the Compton shift. So let us move. Now I will make this formula, this figure now clearly. So I have now used this green color. So I have this is my target electron, right? I assume this target electron is at rest. It's at rest. So if it is at rest, it will have energy just equal to its rest energy, m naught c square, and its linear momentum will be zero, right? So I have a target electron which is at rest. So its total energy is just its rest energy. M naught is its rest mass, c is the speed of light in vacuum. So m naught c square is its total energy, which is its rest energy, and its linear momentum is zero. Now, here comes the incident photon. This is my incident photon. Now, this incident photon has energy E equal to hq. H is Planck's constant, nu is the frequency of the wave, and its linear momentum is h nu by c. Remember, we have a relativistic expression for total energy equal square root of m naught square c raised power 4 plus p square c square. This is the relativistic energy for a materialistic particle which has rest mass. M naught is its rest mass, p is its linear momentum, c is speed of light. So if the momentum of the particle is zero, that means if it is at rest, then E becomes simply m naught square c square, right? C square, you can write c square whole square and square root. When you take the root out, it becomes just m naught c square, which is the rest energy. So when my electron is at rest initially, its total energy is just m naught c square, which is its rest energy, right? Now, for a particle like photon, there is no rest mass. For a photon, rest mass is zero. So this relation reduces to E is equal to Pc. When you put m naught equal to 0, this term will go, it will become E equals square root of P square C square, then you take the root, cancel the root with the square, you get E is equal to Pc. So E is equal to Pc is the relationship connecting the total energy and linear momentum of a particle like photon whose rest mass is 0. So if energy of a photon initially is h nu, its momentum will be E by c, right? Which is h nu by c, right? Things are clear now. So I have a target electron which is initially at rest. So its total energy is equal to its rest energy and its momentum is 0. Now incident photon comes in, hits it. It has energy equal to h nu and its linear momentum is h nu by c. After that, what happens? We use another color. Then what happens? Let me use this color. This photon gets scattered. So this is my scattered photon. As I told you, incident photon loses some energy to the electron. So scattered photon's energy is different. We call that h nu prime. So nu prime is the frequency of the scattered photon. Its momentum will also change because momentum is connected with energy through this relation. So the linear momentum of the scattered photon P is h nu prime by c. So scattered photon energy is h nu prime and its momentum is h nu prime by c. Now in which direction it is scattered, we need to specify the angles. So this is my direction of the incident photon, the direction in which incident photon is coming to hit the electron. Let the angle made by the scattered photon, or the direction in which photon is scattered, with the incident direction, with the direction of the incident photon be phi, right? Now, electron also gets scattered. So, electron gets scattered. I should use some other color. Let me use maroon. So scattered electron gets scattered in some other direction. So this is my scattered electron. This is my scattered electron. Let the direction in which it is scattered makes angle with the photon's incident photon's direction as theta. Now this scattered photon is moving, so it has some momentum. So let its momentum be p. Now it has different energy because now it has some momentum. Previously it had only rest energy. Now its total energy is square root of m naught square c raised to power 4 plus p square c square. Whole thing is in the root. So this is the complete picture. I have a photon which comes with energy h nu and momentum h nu by c. It hits target electron which is at rest. Its momentum is zero. Its energy is just rest energy m naught c square. Photon gets scattered in the direction which makes angle phi with the direction of the incident photon. Scattered photon loses energy. its energy is h nu prime, its momentum changes to h nu prime by c, and the electron gets scattered. It is moving, it has a momentum p, and its total energy is now square root of m naught square c raised power 4 plus p square c square, and it is scattered in a direction which makes angle theta with the photons incident direction. So let us write some equations now. What we are going to do, as I told you, we're supposed to find this shift lambda prime minus lambda. What is lambda prime? Lambda prime is wavelength of the scattered photon, and lambda is the wavelength of the incident photon. So first thing first, as I told you, we will make use of conservation of energy and momentum. So the loss in photon energy is equal to gain in electron energy, because energy is conserved, and loss in photon energy is simply h nu minus h nu prime, because incident photon has larger energy, scattered photon has smaller energy. The loss in photon energy is h nu minus h nu prime, and that is taken by the electron as kinetic energy. So Ke is the kinetic energy of the scattered electron. So let me encircle this equation. This is my equation first. And I told you for a massless particle E is equal to Pc. I named this equation as 2. Second, and I told you P is equal to, for a photon P is equal to h nu by c. Then I can write P is equal to h nu by c. So let me give this equation also a name. This is my 3. So E is Pc for photon. For photon, P is h nu by c initially, right? When its energy is h nu. That's my equation third. So let me move. So I use it here conservation of energy. I will use conservation of momentum. So from conservation of linear momentum. So let me first explain to you the diagram. In this diagram, initially the momentum of the system is only due to the photon because the electron is at rest. Now, after the collision or scattering takes place, the momentum is partly with the scattered photon and partly with the scattered electron. But as you see from the figure, momentum is a vector quantity. When we say momentum is conserved, that means the momentum before the scattering and after the scattering of the whole system is same, because momentum is conserved. But after scattering, the momentum is not in total momentum is not in one direction, it is in the plane. Some of it is in the direction of the incident photon, some of it is in a direction perpendicular to the photon's initial direction. So we need to resolve the momentum into two components. So we will do that. Let me draw a simple figure first. Then we will write equations. So if this is the direction of motion of the incident photon, its energy is sorry, its momentum is h nu by c in this direction. Which direction is this? It is the direction of incident photon. Let me use now another color. Now, scattered photons momentum is in this direction, which is h nu prime by c. So, if you resolve it, that means part of it is in this direction, with which it is making angle phi. So, this part is h nu prime by c cos phi. To make it clear, it is h nu prime by c cos phi, component of this momentum in the direction of the incident photon, and the portion of it is in the direction perpendicular to the direction of incident photon, which is h nu prime by c sin phi. What about the scattered electron? Let me use another color for that. Let me use this color. For scattered electron, its momentum is p in the direction which makes angle theta with the incident direction of the photon. So it makes angle theta here. So in this direction, its momentum is p cos theta, and in this direction, that is perpendicular to the direction of the incident photon, its momentum is p sin theta. So I hope you got this figure. I am saying initially the whole momentum of the system lies with the incident photon, which is h nu by c. So in this direction, the direction of the incident photon, momentum of the system initially is h nu by c. There is no momentum in perpendicular direction. So after scattering takes place, some of the momentum is with scattered photon and some of its scattered electron. A scattered photon has h nu prime by c momentum in this direction, which makes angle phi with the incident direction. So we resolved the momentum. H nu prime by c is the momentum of the scattered photon in incident direction, and h nu prime by c sin phi in perpendicular direction. And the electron's momentum we have resolved as p cos theta in the direction of the incident photon and p sin theta in a direction perpendicular to the incident photon. Now let me use this conservation of linear momentum to express the uh, momentum conservation. So let me write the equation. So in the original photon direction, in the original photon direction, as I told you, the total momentum initially before the scattering is just h nu prime h nu by c. So we have h nu by c. I can write plus 0 because initially electron has no momentum in any direction, right? Then it must be equal the momentum of the system in the same direction. Now the momentum of the scattered photon in this direction, incident direction, is h nu prime by c cos phi, and the momentum of the electron in the incident direction after scattering is p cos theta plus p cos theta. So we have used momentum conservation in the original direction of the photon. So let me name this equation as equation 4. This equation is clear, so don't get confused. H mu by c plus 0 is the momentum of the system in this direction before scattering. H mu prime by c cos phi plus p cos theta is the momentum of the system after scattering in the direction of the incident photon. We have, let me write first another equation, then I will explain to you another thing. Let me use maroon. Now, in the direction, I should say, in the direction perpendicular to the incident direction, in the direction perpendicular to the incident direction, that means this direction, right? What is the initial momentum of the system? That is zero, because electron is at rest, photon is moving in this direction, so it has no momentum in perpendicular direction, so it is zero. What is the momentum of the scattered photon in the perpendicular direction? It is h nu prime by c sine phi. What is the momentum of the scattered electron in the perpendicular direction? It is p sine theta, but here you have to write minus. Let me explain it. It is understood, still I will explain. I name it equation 5, right? So you see, when we used momentum conservation in the original photon direction, these momenta h nu prime by c cos phi and p cos theta were similarly directed. P cos theta is this way, h nu prime by c is by cos phi is also to the right, but in perpendicular direction h nu prime by c sine phi is upward, but p sine theta is negative. That is because it is downward pointing. So that's why here we have minus and here we have plus. This is all we have. We have these equations from conservation of energy, from conservation of momentum. So our next step is what? We have to use equations 1, that is the equation from conservation of energy, and equation 4 and 5, which we got from conservation of momentum, to find a formula that relates the wavelength difference between incident and scattered photons with the angle phi between their directions, right? That's our purpose, which I told you on the first place. We have to find the this difference, Compton shift, lambda prime minus lambda, right? That we will do in the next lecture. I hope it is clear. We will continue from this. Don't forget, I stop here and we will continue in the next lecture. Don't forget to like, share, and subscribe my channel. You can give comment in the comment box. Thank you. God bless you. Assalamu alaikum.